50-year-old physics theory proven for the first time with electromagnetic waves. Physicists at the University of Southampton have successfully tested and confirmed a 50-year-old theory for the first time using electromagnetic waves. Their experiments demonstrated that the energy of waves can be amplified by bouncing, twisted waves, waves with angular momentum, off a rotating object under specific conditions. This is known as the Zeldovich effect, named after Soviet physicist Yakov Zeldovich, who developed a theory based on this idea in the 1970s. Until now, it was believed to be unobservable with electromagnetic fields. The Zeldovich effect works on the principle that waves with angular momentum, that would usually be absorbed by an object, actually become amplified by that object instead, if it is rotating at a fast enough angular velocity. In this case, the object is an aluminum cylinder and it must rotate faster than the frequency of the incoming radiation, explains a research fellow at the University of Southampton, Drive. Marion Crom. Colleagues and I successfully tested this theory in sound waves a few years ago, but until this most recent experiment, it hadn't been proven with electromagnetic waves. Using relatively simple equipment, a resonant circuit interacting with a spinning metal cylinder, and by creating the specific conditions required, we have now been able to do this. Quote. The scientists' findings are published in the journal Nature Communications. Connection to the Doppler effect. The Zeldovich effect is difficult to observe, but has links to a well-known phenomenon called the Doppler effect, which we all experience around us every day. Imagine you are standing on a busy road and a police car races towards you with its siren going. From your perspective, as it approaches, the siren sounds higher pitched than when it has passed. This is because the sound waves in front of the car coming towards you are compressed, at a high frequency, hence a higher pitch. Behind the car, as it moves away, they are more spread out at a lower frequency, resulting in a lower pitch. This is the Doppler effect. This can also be applied to light waves. In fact, astronomers use it to understand whether a planetary body is moving towards, or away from the Earth, according to the frequency of the light waves seen from their point of observation. A similar, rotational Doppler, frequency shift happens for twisted waves and relative rotation. In the Zeldovich effect, the metal cylinder needs to rotate fast enough that from its perspective it sees a twisted wave shift in angular frequency, so much that it actually goes to a negative frequency. This changes the way the wave interacts with the cylinder. Usually the metal would absorb the wave, but when the wave frequency goes negative, the wave is in fact amplified, reflecting off the cylinder with more energy than when it approached. The condition for amplification is from the rotating perspective of the object, explains Marion Crom. Twisting electromagnetic fields hitting it have become rotationally Doppler shifted, so much, or so low, that they've gone through zero and into a negative angular frequency. Negative frequency then means negative absorption, and this means amplification. Quote. Implications and future research. The scientists say that proving the Zeldovich effect in different physical systems, both acoustics and now electromagnetic circuits, suggest that it is quite fundamental in nature. Electromagnetic tests also pave the way to observing the effect on a quantum level, where the waves could be generated by the cylinder amplifying the quantum vacuum.